Good day, everyone. My name is Ajimanesta Safo, and this is my presentation on adaptive integration. This is my content. We start off with the background. So integration is the calculation of the area under a function, and the integral works in many cases to achieve this, but there are moments when an integral cannot be evaluated analytically, or when the integrand is complicated, discontinuous, or highly oscillatory. In such cases, we have classical methods like the trapezoidal rule or Simpson's rule, which can be adopted, and they require subintervals to achieve high accuracy in some circumstances, and this can actually be a bit cumbersome, so Gauss quadrature provides a more efficient alternative. And so it provides an alternative where it approximates the integral by choosing the best possible nodes and choosing optimal weights, and it uses this formula where it takes the sum of the product of those weights and the function at those nodes, and then by so doing it aims to approximate the integral, and this method is supposed to be a bit easier than classical methods like the trapezoidal rule and the Simpson's rule. Now we come to the Legendre polynomial. This polynomial is relevant when calculating the nodes of the Gauss quadrature. So it's related to the Gauss quadrature. And for an endpoint Gauss Legendre quadrature, the nodes are always the roots of the Legendre polynomial. What this means is that in generating the formula for the Gauss quadrature, we need nodes and we need weights. To calculate for these nodes, we use the Legendre polynomial, and the relationship between the Legendre polynomial and the Gauss quadrature is that the roots of the Legendre polynomial are the nodes of the Gauss quadrature, which is these xi's that we see in this equation. Now we've established how to calculate for the nodes that are needed for the Gauss quadrature. Next is how to calculate for the weights that are needed in the Gauss quadrature formula. To do that, we use the Lagrange polynomial. It's a polynomial that matches the function Gauss seeks to approximate, which is f of x, at the Gauss nodes xi. It's of the form the sum of the product of that function at the Gauss node times the Lagrange polynomial. Now, what happens is that this Lagrange basis polynomial is a product of these sets of expressions. We will look at how this comes into play as we move on. So this is the relationship between the Lagrange polynomial and the Gauss quadrature. The Lagrange polynomial provides the weights for the Gauss quadrature to be able to approximate the integral of the function that it seeks to integrate. So although Gauss quadrature is meant to assist us when the classical methods are more difficult to use, it can also fail. For instance, it can fail when the function changes behavior. It can fail in intervals where the function changes behavior, or where there are discontinuities, or where there are sharp peaks, or where the function isn't smooth. So in such circumstances, we use adaptive Gauss quadrature. And what adaptive Gauss quadrature does is that it automatically subdivides the interval, and then it estimates the error by comparing the coarse and fine approximations. Then it focuses computation only where needed until the error is tolerable. So what adaptive Gauss quadrature does is it automatically subdivides the interval, then it focuses on calculating for the integral in the subdivided sections, then it puts all of them together, then it compares that value to when it did the integration over that interval without the subdivision. It compares these values and then it checks for the error, and then if the error is tolerable, it ends there. But when the error is not tolerable, it continues to subdivide until the error is tolerable. And so by doing that, it aims to create an accurate, efficient, and robust integration method. Now we move on to our questions. The first question states that, given that the cubic Legendre polynomial is P3 of x is equals to half x, open bracket, 5x squared minus 3, derive the 3-point Gauss quadrature rule on the interval -1 to 1, by evaluating the relevant integrals by hand. Demonstrate that this quadrature rule integrates all polynomials up to the expected degree exactly. So this question is in two parts. We are to derive a 3-point Gauss quadrature rule on the interval -1 to 1, and we are to do this by hand. And then the second point says we should demonstrate that this rule integrates all the polynomials up to the expected degree exactly. Now the first question is that what's the function that we want to integrate? The answer to that is we do not have the function to integrate yet. This P3 of x is not the function we are integrating, but it's the Legendre polynomial that will provide the roots for our Gauss quadrature rule to be able to integrate the functions to be given in the next questions. So that is what we have right now. We do not have the function we are to integrate. We only have the Legendre polynomial that is to provide the roots to the Gauss quadrature rule, so that we can generate it and use it to integrate the functions we will be given. And then this is our interval which we'll be integrating over. It's -1 to 1. And then the second part of the question is saying to demonstrate that this quadrature rule integrates all polynomials up to the expected degree exactly. So if you remember from the previous slide, it mentioned that when you have an n-point Gauss quadrature, it's supposed to be able to integrate up to 2n-1 order of polynomials exactly. What this means is that if we have 3-point Gauss quadrature, it should be able to integrate up to 2 into brackets 3 minus 1 order of polynomials exactly, and this will give us 5. So what that means is that if we have our Gauss quadrature, our 3-point Gauss quadrature rule, after we have finished getting this rule, it should be able to integrate all polynomials up to the order of 5 exactly. That's what that part of the question is asking us to demonstrate. So we'll go right into the solution. So the 3-point Gauss quadrature rule that we've been asked to create is of the form integral from -1 to 1 of f of x dx approximately weight 0 multiplied by function at x0 plus weight 1 multiplied by function at x1 plus weight 2 multiplied by f multiplied by function of x2. So we need to solve for the missing nodes x0, x1, x2 and their corresponding weights w0, w1 and w2, so that we can express the Gauss quadrature rule in the form in which it is written, in this form. So what we are going to do is to find for w, all the w's and all of the x's. Okay. So first of all, we start by trying to solve for the x's, which are the nodes. And as mentioned earlier, to solve for the nodes, we use the Legendre polynomial, and we've been given our Legendre polynomial. So as mentioned earlier, the nodes are always the roots of the Legendre polynomial. So we are going to solve for the roots of the Legendre polynomial P3 of x, so that we can find the nodes that we need to write the Gauss quadrature rule. To find for the roots, we set P3 of x to 0. So P3 of x is equal to half x into bracket 5x squared minus 3. We equate that to 0, and all this comes to 0, which means half 5x cubed minus 3x will be equal to 0. This implies that 5x cubed minus 3x equal to 0, and then solving the cubic equation, we get these values for the nodes, which are x not equal to 0, x1 equals to minus root 15 on 3, and then x2 will be equals to positive root 15 on 5. So this is what we have for our nodes. Our next step is to solve for the weights. In solving for the weights, we approximate f of x, which is our unknown function, with a polynomial that matches the function f of x at these Gauss nodes. Then we integrate this polynomial and compare with the Gauss formula to extract the weight. That means we need to have this function that we need to match our function at x. Then after that, we will now integrate that function. And since Gauss quadrature rule is supposed to integrate that function. We can compare the two equations, then we can extract our weight from that equation. I'll explain what this means as we move along. So the unique polynomial that matches f of x at the Gauss nodes x0, x1, x2 is the Lagrange interpolating polynomial, as we mentioned earlier, that the Lagrange interpolating polynomial is related to the Gauss quadrature rule in that it matches the function Gauss quadrature rule is trying to integrate at the Gauss nodes. And so that's why we come back to this. So the polynomial that we are going to use to get our weights is of the form P2 of x is equals to the sum from I equal to 0 to 2 of the product of f of xi and lix, where lix is a Lagrange basis polynomial. Okay, so since we are saying that P2 of x is actually the function, it's actually the polynomial that matches our f of x at the Gauss node, that means we are essentially saying that that function f of x is equals to P2 of x at the Gauss nodes. And that means that if we integrate f of x, that should be equal to the integral of P2 of x over the same interval. And we have our expression for P2 of x being this, which means if we integrate P2 of x, it should be the integration of that expression. And expanding that integration of that expression, we get this expression. And by linearity, this expression is equal to, when we factor out the f of x's out, and we are left with the integration of the Lagrange basis polynomials only. So like this, plus this, plus this. And comparing that with the Gauss formula, we can see that they have something in common. We have our f of x not here, and we also have it here. We have our f of x1 here, we also have it here. And we have our f of x2 here, and we also have it here. So it implies that w naught is actually the integral of L naught of x dx over minus 1 to 1. W1 is our integral of L1 of x dx over minus 1 to 1. And W2 is equals to our integral of L2 of x dx over minus 1 to 1. So as implied by the previous slide, if we integrate these three expressions, that will give us our weights W0, W1, and W2. So we can see that to calculate for W0, we have to integrate from minus 1 to 1 of L0 of x at dx. Now, L0 of x, as we saw earlier, it's called a Lagrange basis polynomial. And to calculate for that, we do the product of x minus all the other nodes apart from the node we are at, all over the node we are at, minus all the other nodes apart from the node we are at. So that's why we have x minus x1 all over x0 minus x1 times x minus x2 all over x0 minus x2. So if there was an x3, then it would have been times x minus x3 all over x0 minus x3. And then putting in the values for the nodes, we have this expression. Then it eventually comes down to this. So this is the expression we have for our Lagrange basis polynomial. So we get that expression. I'll put this expression into our integration. And after integrating, we come down to 8 out of 9 for the value of our W0. So that will be our first weight. So this is the weight that we would use to calculate for our integral in the Gauss quadrature rule. But then this weight will be working together with our first node, which is x0. Then we go to the next one. The next one, which is W1, also follows the same pattern. And the final result for W1 is also 5 out of 9. Then the next one, W2, we calculate for that, and the final result of that is 5 out of 9 also. Then this will be our final solution. Since we have our x0, x1, x2, we have our w0, w1, w2, we put that into the Gauss quadrature, 3-point Gauss quadrature rule that was written before, and we get these values. Now, to prove whether it integrates all polynomials up to the expected degree exactly, we integrate an arbitrary fifth order polynomial on the minus 1 to 1 interval, and then we now use our Gauss quadrature rule when we compare the two answers to see if the answers are correct. So what this means is we are simply going to integrate a a fifth order polynomial of this form, because all other fifth order, any kind of polynomial that will be of the order 5 or below, will be a combination of any of these values. So if we're able to integrate this accurately with the Gauss quadrature rule, then we can say that all polynomials of the order 5 or below can be integrated using our generated Gauss quadrature rule. So that's what we are going to do. So we integrate this normally, integrate this with our Gauss quadrature rule, compare the answers, and if it's equal, then we have done what the question is demanding of us. So when we integrate this using the normal integration, this is the final answer that we come to. So as we can see here, the value that we got for the integration on the previous slide is equivalent to the value that we got after using the 3-point Gauss quadrature, which shows that our 3-point Gauss quadrature rule is accurate. It actually integrates up to the expected degree exactly for all polynomials of the order 5 and below. So since the rule holds, then it is correct for all polynomials up to the 5th order, since all such polynomials are a combination of p5 of x. Okay, so this is the second question. Because of time, I will not read the whole question, but I'll explain the question. So this question is actually asking us to apply adaptive Gauss integration using the Gauss quadrature rule that we actually generated from the beginning. So it is telling us that we should use the 3-point quadrature rule to integrate f over an interval a to b, and then this IAB will be that integral. Then it's telling us to divide up the interval by defining c, which is equals to a plus b on 2, and then we have to now apply adaptive integration, whereby we divide the interval and then do the integration for each of the sections of the interval, and then the final integration of those two sections will now be this new integration, which was based on the subdivision, so not the whole. So that means this IAB will be the integration that we do over the whole interval without any subdivisions. Then this integral with the hat will be the integral of the subdivisions all put together. So that's actually how we are going to go with this question. And then the error here is the absolute value of the integration that was done without the subdivisions minus the integration done with the subdivisions. And then now, if this error is less than the tolerance level that we actually set times the length of the whole interval, then the error is acceptable and the method can terminate. But if it is not, then it will be subdivided and subdivided until our error is less than the tolerance level. So that is what this question is telling us to do. So in short, this question is telling us to apply adaptive integration using our 3-point quadrature rule. Then we have to write the function to implement this adaptive integration scheme using t equals to 10 raised to the power minus 6, and we have to apply it to this interval, to this integral for m equals to 4, 5, 6, 7, and 8. And then for each case, you have to report the value of the integral and the total estimated error by summing the relevant error terms and the total number of intervals that are used. So after running the code, these were the integral values for each of the m's. M of 4 had this value, m of 5 had this value, m of 6 had this value, m of 7 had this value, and m of 8 had this value. And if you observe, you see that for m of 4 and 5, we had 1, 1 as the number of intervals, which means that when the quadrature rule was applied without any subdivision, it got the integral value at the first interval. And this is actually accurate because our quadrature rule was proven to be able to integrate up to the order of 5. And since 4 and 5 are within that range, it should be able to do the integral over the first interval. So this is accurate. And then these were the number of intervals for 6, 7, and 8. Then for the final part, we were to use our adaptive integration routine to evaluate these 3 integrals and record the same values as before. And these were the values that were gotten for each of those functions. So according to the question, we use our Gauss quadrature rule to calculate for our integral, and then these are actually the values that we calculated for by hand, our weights and our notes. And then after we've gotten the final answer for our Gauss quadrature, so after we've gotten our I from the Gauss quadrature that on the previous slide, we now calculate for the integral using Gauss quadrature on the subdivisions, which is IL and IR in this case. And then we check for the absolute value of the subtraction of the new integral minus the old one, which is the error that we have been asked to calculate for in the question. Then this error is now checked whether this error, now we check whether this error is going to be less than the tolerance times the interval. If it's less than it, we've ended. But if it's not less, we keep subdividing, and then we keep calculating for more and more integrals across the new subdivided intervals until our error is less than the tolerance. Then it ends. And the values that are returned are the values that were requested for in the table, which are the integral value, the error value, and the number of subintervals. And then this is the code where we call in our adaptive integration to work using these particular functions that were given to us in question number B, question C, the first function, and then question C, the second function, and question C, the third function. So these are the codes that were used in solving for B and C. So the conclusion is that Gauss quadrature may not always achieve accurate integration results, especially with an unpredictable function. But with Gauss adaptive Gaussian quadrature, we can integrate such functions by focusing on dividing the significant areas until the error is tolerable. Adaptive Gaussian quadrature is like a smart calculator for integration. Thank you.